All right, hello and welcome back to another video. In this video, we're going to work on problem number 3 on worksheet number 2, which is just dealing with domains of rational functions and radical functions. So this is going to be a very quick video just dealing with how to find the domain of these types of functions. So we have 3 problems prepared for this, and then you can try these other problems on your own. So let's go ahead and take a look at this video here. So this video is just meant to be a quick summary of how to find the domain of these kinds of problems. And so I'll give the general idea for this. And so in green here, we'll say if we have a rational function, let's call it r of x. A rational function is just a function that has a function in the numerator and a function in the denominator. I'll call them n of x and d of x. And so the problem with this function arises when the denominator function is equal to 0, because we can't divide by 0. And so then if we can't divide by 0, we should not have the denominator function be equal to 0, because that would cause us to divide by 0. So we say here that d of x, the denominator function, should not be equal to 0. And so to find the domain, we just need to exclude the values where d of x is equal to 0. Okay, so here is a function in green called g of x. And let's give the function g of x equals 2x plus 8 divided by 3 plus, and let's put 3 plus 5x. Okay, let's modify it just a little bit. So what values of x cannot be plugged into this function? Well, I could try plugging in, just a number like, let's see, g of 1. Let's see if 1 is part of the domain. We can plug in 1 by 2 times 1 plus 8 divided by 3 plus 5 times 1. This is 10 on top and 8 on the bottom, which reduces to 5 over 4. And so we have an ordered pair, 1 comma 5 fourths. This element in the domain, 1, was paired with exactly one element of the range, 5 fourths, and it's perfectly normal behavior for a function. Now we get to the question of, well, are there any elements that cannot be plugged in or cannot be inputs for this function? And the answer is yes. The answer is, that we should check the denominator and see if it's ever equal to 0. So we get our denominator, 3 plus 5x. We set it equal to 0, and we can solve this by subtracting 3 on both sides. This gives us 5x equals negative 3, and then dividing by 5 on both sides. This gives us x equals negative 3 fifths. This value here makes the denominator 0. So we don't want this value as part of the domain. We can't have it as part of the domain. You could try to plug this number in, but it's not going to give you, let's try it here. G of negative 3 fifths. You say, hey, well, why are you excluding negative 3 fifths? What did it do? Well, we can plug it in, and we get 2 times negative 3 fifths plus 8 divided by 3 plus 5 times negative 3 fifths. And if we work out the bottom, we can see that the 5s are going to cancel, and we're going to get 3 plus negative 3 on the bottom. And so that is going to result in getting negative 6 over 5 plus 8 divided by 0. And here, that division by 0 is a big no-no, right? We don't want that. And so this is actually called undefined. This function is not defined when x is equal to negative 3 fifths. So since this element If we were to put it in the domain, it should be paired with an element in the range. But since when we plug it in, we don't get an output value, it can't be part of the domain. And so our domain is going to be all real numbers except for those that make the denominator equal to zero. For a basic rational function where you have a polynomial divided by another polynomial, we are just going to take all real numbers. We know that all real numbers, let me write all real numbers here, negative infinity to positive infinity. That's all real numbers, but we just said negative 3/5 cannot be part of the domain. So we're going to modify this and say all real numbers except for negative 3/5. So we go from negative infinity all the way up to negative 3/5, and then exclude, use the round parentheses to exclude negative 3/5, union negative 3/5 to positive infinity. This is the domain of that function. Okay, there we go. So that's whenever you have a nice rational function, meaning a polynomial divided by another polynomial, we only care we only want to restrict the denominator from being equal to zero. Sometimes students will say, well, hey, what about x equals, let's say, negative 4? That's going to make the numerator equal to zero. Well, that doesn't actually matter in terms of the domain. We're fine with the numerator being zero because a zero can be divided by another number. Zero divided by a non-zero number is equal to just zero, and that's fine. There's no that's a real number. But dividing by zero does not produce a real number. That's actually undefined. So x equals negative 4. Um, negative 4 would actually be paired with zero, and that's a fine ordered pair. So zero is part of the domain. What we don't want is the numerator, or sorry, the denominator expression to be equal to zero. Negative 3/5 causes that in this case, so we'll exclude negative 3/5 from domain. All right, nice. So you can try part B now on your own. Um, that's very similar. So you can try that one. The answer will look very similar. Oh, part B and part A, both of those you can now do. Now let's go ahead and take a look at radical functions. We just looked at rational functions. So that was rational in green. Next, we can look at radical functions. And if you watched the previous video, we already talked a little bit about radical functions. Radical. Uh, that was over here if you watched the previous video. How to find the domain of a radical function, like f of x equals the square root of x plus 4. We did that in the previous video, but we'll do it again here. This one's a little bit more complex, but it's the same kind of idea. With radical functions, we run into a problem with the square root whenever we try to take the square root of a negative number. In this class, we will not be taking square roots of negative numbers. We will say that the square root of a negative number is not a real number. And so we cannot take, when we take a square root, the square root of whatever we're taking the square root of needs to be not or non-negative, not negative. What's another way that we could say something is not negative? If we want 3 minus 5x to not be negative, then it needs to be either positive or equal to 0. And so we are going to take this radicand. Let's see, did I write it in words earlier? Yeah, if we're going to take this radicand, the inside, I'll maybe write it like this. The inside, it's called the radicand, that's the official name, but we're going to set it greater than or equal to 0 and solve that for x. That is going to give us the x values that make that inner expression positive or 0. And positive numbers and 0, we can take the square root of perfectly fine. So to find the domain of this function, we will just take 3 minus 5x, set it greater than or equal to 0. And we should use the greater than or equal to symbol to do this Sometimes students want to use the equal sign just by itself. I would not recommend just using the equal to symbol, but the greater than or equal to symbol. And we'll see why in just a moment. When we try to solve this for x, we're going to get a negative 5x is greater than or equal to negative 3. Now, here's the reason that we want to use the greater than or equal to symbol, because when we divide an inequality by a negative number, you know that that inequality needs to flip around and become instead less than or equal to. So if it's greater than or equal to begin with, we divide both sides of the inequality by a negative, that symbol flips around and becomes a less than or equal to symbol. And we get 3 over 5. Oh man, did that almost come out to the same number? Oh, negative 3/5. Huh, I didn't plan that. Okay, so in order for that inside expression to not be negative, to be greater than or equal to 0, we must have that x is less than or equal to 3/5. And so in interval notation, that is less than or equal to 3/5. That is going to be to the left of 3/5. So that is going to be to negative infinity all the way up to 3/5, including 3/5 because we have that or equal to symbol there. Okay, so this is the domain of this radical function. We can plug in any number to the left of 3/5. And I can try one as an example. If you saw the previous video, then you would see that we plugged in some numbers. This is going to be a little bit complicated because um, yeah, these numbers are not super nice. But let's see if we can find one. So we want a negative number, or sorry, a number that's less than uh, 3/5. So I'm going to try plugging in. And with these square roots, it is, well, even with this one here, we saw one where the numbers weren't very nice because I didn't make this. We're not asked to graph this, so we're not really needing to plug in. We're essentially done in terms of finding the domain. Um, yeah, let's plug in a negative 1/5. How about that? So a little bit of extra thought needs to go into this. But if we plug in negative 1/5, then that negative 1/5 is, less than 3/5. So it should be okay in general to plug this in. The square root of 3 minus 5 times a negative 1/5. And notice that a negative number, well, hey, that's going to cancel out this negative out here. So we can see why negative numbers are allowed, because that's going to cancel out with that negative, making the entire radicand positive, which we can take the square root of positive numbers. The 5s are also going to cancel, so we're going to get 3 plus 1, and the square root of, 3 plus 1 is 4. The square root of 4 is 2, and so we have the ordered pair, negative 1/5, comma, 2. Hey, that was nice. We picked a number that is in the domain, and it was paired with exactly one value in the range. Um, yeah. Try to plug in a number greater than 3/5, and it will not work. You can actually try, mentally just to plug in a number greater than 3/5. That's like 1 or anything greater. The number 1, if you plug it in just mentally, 3 minus 5 times 1, well, 5 times 1 is 5. So 3 minus 5 is negative 2. The square root of negative 2 is not a real number. So that's why 1 is not in the domain. Okay, so let's go ahead and continue on to the next problem. Didn't want to make this video too long. So in this worksheet, we also have some functions that are combinations of fractional functions and radical functions. So we'll take a look at one example of that. So after doing that problem, you should now be equipped to do parts C and D of our worksheet here. And so, but let's take a look at something similar to E and F. So what if we have a square root function, a radical function, And there's some other part here, the square root is in the numerator, and there's a denominator as well. Well, let's take a look at them one at a time. And we should start with the radical. That's what I would recommend doing. So we know that this radical function needs to have its inside larger than or equal to 0, greater than or equal to 0. So we can start with this. So just starting off, well, we can assume that, the biggest domain that could occur would be negative infinity to positive infinity. As soon as we see a radical, a square root, it's likely that the domain is going to be reduced from negative infinity to positive infinity. So, it's probably not going to be that. Let's see what x minus 2, what is required for x minus 2 to be larger than or equal to 0. Well, we can solve this. We add 2 to both sides. So that means x must be greater than or equal to 2. Okay, so that has now reduced my potential domain to the numbers from 2 to positive infinity, right? Because x now needs to be larger than or equal to 2 to be able to be plugged into the square root. Okay, well, that's the restriction that comes from the radical, the square root. But there's also a denominator. And we know, let me switch colors here. We know that the denominator, 2x minus 5, cannot be equal to 0 because we can't divide by 0. So let me set it equal to 0 and figure out which x value would cause that to be 0. We can add 5 to both sides. So 2x is equal to 5. Divide by 2 on both sides. And so x is equal to 5 halves, which is the same as 2.5. So 2.5 is going to make the denominator 0. So we need to exclude it as part of the domain. It is inside of this set here, so let's go ahead and kick it out. The final domain here, the final answer, or the domain of this function is going to be, well, 2 is fine. Anything greater than 2, except for 2.5 is fine. So we're going to make and maybe this would be easier to see on a number line. So far we're at 2 to infinity, but 2.5, we need to kick that one out, right? And so our domain is going to be everything from 2 up to 2.5, but we will not include 2.5. And then, or it can be in the set from 2.5, not including 2.5, to infinity. Okay, notice how this 2 to infinity just kind of got morphed a little bit. We just kicked out one number, 2.5, and this is now the domain. Well, it always has been the domain, but we've found the domain to be this. All right, and that is, essentially how it's going to go for parts E and F. You need to find out, well, what's the restriction caused by the square root? And then if there's also a fraction, what's the restriction caused by the denominator of this fraction? And put those restrictions together, that is your domain. All right. Hope you enjoyed that. We'll see you in the next video.